Okay, here's part 2 of the lecture on simple circuits. Let me first of all here briefly introduce you to both series and parallel circuits. Now, when covering capacitance, I introduced you to series and parallel circuits in that context. Now I'll do so here in the context of conventional current flowing within a circuit. Okay, let me begin first of all with a parallel circuit. Okay, so let me now go ahead and draw two resistors that are here in parallel. Like so, where I have a potential difference V. Let's say that the resistors each have individual resistances, we'll say R1 and R2. Like so. Okay, and now the conventional current I flows through the circuit. And then notice that the conventional current here encounters what is referred to as a junction. When it encounters a junction, it splits into two parts. So for example, flowing now through this branch, as we say, of the circuit, is going to be a current I1, and then flowing through this branch of the circuit over here is going to be a current I2. The sum of the two, I1 plus I2, is equal to the original conventional current I. This is cleverly known as junction rule. Junction rule basically states the following: the amount of current flowing into a junction has to equal the amount of current flowing out of a junction. If they weren't equal to each other, that would be an obvious violation of conservation of energy. So the amount of current I that's flowing into this junction right here, that then splits up into I1 plus I2. Okay, notice that the same thing then occurs over here at this junction. The I1 and I2 come back together to produce the original current I, which is flowing like so. Okay, now what happens to the overall resistance in such a circuit when you then hook up, say, resistors in parallel to each other? Well, the amount of resistance overall goes down. And the reason for that is because you're basically providing more branches for the current to flow through. It's like taking a stream of water, for example, and widening the stream. If you widen the stream, you make it easier for the current to flow, therefore the resistance goes down. Here's how we can show this mathematically. Okay, now recall that straight lines drawn like so on a circuit diagram are equipotential surfaces. So all of this is at the same potential. And then down on the lower half of the diagram, all of this is at the same potential. Therefore, if the potential difference from here to here is the voltage V of the battery, that is then therefore the potential difference here and here, and also the potential difference between here and here. So the voltages V across each of the batteries is exactly the same, or across each of the resistors, excuse me, is exactly the same. So now let's go ahead and replace all of these guys here with Ohm's law. So first of all, the current I, I'm going to write as the voltage V divided by what is referred to as the equivalent resistance. And then on the right-hand side, we have the same voltage V and then divided by resistance R1. And then right here is the same voltage V divided by resistance R2. Once again, the voltages across each of the resistors is the same as that of the battery, because all of this is an equipotential surface and all of this is an equipotential surfaces. Okay, notice that the V's all cancel out, like so, and you end up with an expression that is written like this. Overall, the equivalent resistance, R equivalent, is less than the sum of R1 and R2. And the reason for that is because you basically are widening the stream by adding more and more branches then to the circuit. When you add more and more branches to the circuit, you make it easier for the current to flow. So then therefore, for a particular potential difference V, the amount of conventional current increases. You'll see this in one of my mathematical examples a little bit later on here in the lecture. Okay, now let me go ahead and demonstrate for you a parallel circuit. I'll do so in the following way. So I'm going to plug this series of light bulbs here into the electrical outlet. And then I have a switch here that allows me to switch back and forth between parallel and series. Right now, the two light bulbs here are hooked up in parallel. Basically, the circuit diagram looks like this. The amount of current that's flowing through here, I, is a large number, because ultimately the resistance, R equivalent, is a low number. Okay, now most of the devices that you have in your home are hooked up in parallel with respect to each other. There are some obvious advantage in doing this. For example, I could, turn one of the things off, like so, and when I do, it's like I close, or rather opened, this portion of the circuit, so there's no longer any current flowing through this. There's only current flowing through this loop here with the single light bulb. However, the more things that I turn on, like so, the lower the resistance, and then therefore the greater the amount of the conventional current that flows. There are some dangers associated with this. I'll get to that a little bit later in one of my examples. Okay, next let me show you the basics behind a series circuit. Okay, so in a series circuit, you basically just have one resistor after another within a single loop. So right here is my potential difference once again. V, and then right here is my resistor R1, and this right here is my resistor R2. The conventional current I flows. Okay, when you hook up resistors in series, as I've done here, it's like you're adding more and more bumpers, if you will, in your pinball machine. So then therefore the resistance increases. Here's then how we can write this mathematically. Okay, now this right here is an equipotential surface. This right here is an equipotential surface. So the potential difference V between here and here is the same as the potential difference between here and here. But notice that I have another piece of metal in between here and here, and that's right here. This then means that this total potential difference V here has to be the sum of this potential difference, call it V1, and this potential difference, call it V2. Think of it in terms of height. Let's say that this right here is a total of, say, 10 feet. So then therefore, if this right here is 5 feet and this right here is 5 feet, 5 plus 5 is equal to a total of 10 feet. Once again, if you have trouble picturing voltage, always just think of it in terms of differences in height. So the voltage V is equal to V1 plus V2. And now I'm going to replace these guys here with Ohm's law. When I do, it's the same amount of current I that's flowing through the circuit. So this right here on the left-hand side of the expression is I times R equivalent. And then on the right-hand side, we have the same I times R1 plus the same I times R2. And then notice that the current I cancels out. Like so. So then therefore, the equivalent resistance is R1 plus R2. So it's like you're just simply adding more and more bumpers, if you will, into your pinball machine. And when you do, this then means that the resistance increases. There are some advantages to doing this in particular circuits. Now I can demonstrate that here with means of my light bulbs. Okay, once again, this is when they're in parallel. And then by flicking this switch here, here's the bottom of the board, by the way. When I flick this switch here, now they're in series with respect to each other, and you can see that the bulbs are a lot dimmer. So the reason why the bulbs are a lot dimmer is because it's the same potential difference V the whole time, but now I've increased the resistance by placing the light bulbs here in series with respect to each other. So if I place then the light bulbs in series, then the amount of conventional current goes down. That's why the bulbs are not nearly as bright as they were earlier in parallel. However, there are some disadvantages to doing this as well. For example, if I unhook one of the light bulbs, now I've broken the circuit completely. It's as if I just did something like this in doing so, and now no current is able to flow. So that's the basic idea behind a series circuit. Okay, I'm going to finish here with giving you a brief description of what is meant by alternating current. In order for me to do so, at this point, what I want you to do is pause this lecture and then take a look at the 2 short demonstration videos that I've posted for you in the folder. Alternating current demonstrations, parts 1 and 2. Go ahead and take a look at those 2 demonstrations right now, please. Okay, now that you've taken a look at those two demonstration videos, let me give you a basic understanding as to what is meant by alternating current. Okay, now with alternating current, supplying the potential difference is not a battery. Instead, we have what is called a generator. For example, in part two of my demonstration, I showed you a hand crank alternating current generator. The generator symbol is drawn like so. There's a little sine curve here for reasons as you'll see. And then let's say that I have my little hand cranked generator hooked up to my light bulb in my demonstration, and then right here is a resistance R. Okay, alternating current is graphed out in the following way. What we do is we graph the current itself as a function of time. When we do, you end up with a sine curve, which looks like this. This right here is one complete oscillation, so then therefore along the time axis, that right there is the period of the oscillation. And then the amplitude of this curve here and here, this is referred to as the peak current, and this is written as I0, positive and negative. Now, as I mentioned in part one of my demonstration lectures, for alternating current, worldwide there is a standard associated with the frequency of that current. The frequency of that current is equal to 60 hertz. This is a standard that is used worldwide. The period of the oscillation is the reciprocal of this value. This is 1/60th of a second. Notice that this time here matches the amount of time that is measured on our spark timers when we use those, for example, in various laboratory exercises back in the first semester for mechanics. That's not a coincidence. The reason why the time on the spark timer is 1/60th of a second is that's because the alternating current itself that it's plugged into has a frequency of 60 hertz associated with it. Okay, now it's a little bit difficult to picture exactly what is happening with alternating current. Here's what's not happening. What's not happening is that the current is not doing this. It's not going from the generator to the other side and then back again like so, 60 times per second. That's not what's happening. Instead, what's happening is as follows. If you could examine a small portion here of the wire, what you would find is that the actual electrons themselves are going back and forth like this with a very small amplitude, 60 times per second. It's like you're taking your pinball machine, for example, and you're basically having it oscillate like this 60 times per second. That's occurring at all points here within the wire itself. So the actual distance that the electrons travel in this oscillation is really small, so they do not go from the generator and then back again like so. Instead, over a very small distance along each section of the wire, the electrons themselves are basically oscillating back and forth like this, 60 times per second. That's what's happening in alternating current. Okay, now through Ohm's law, the voltage associated with the generator or across the resistor, etc., ultimately traces out the same graph. So the voltage as a function of time also traces out a sine curve like so from Ohm's law. This right here is one full period. This point here and here, this is referred to as the peak voltage, and this is referred to as V0. Okay, what we do is we calculate a mathematical average of these graphs. It's not necessary for us to do that here in this class. It's actually something that we save for AP Calculus. When we do calculate the average of these graphs, we end up with what are called root mean square values of the voltage and of the current. This is referred to as VRMS. The RMS stands for root mean square. It's a mathematical average that involves integrating over these curves. The RMS voltage, this is the voltage that comes out of a wall socket, for example, is a standard in the United States. It's 120 volts. There are, however, some other countries around the world, like for example in Europe, where as a standard they still have the frequency as 60 hertz, but as a standard in Europe, the RMS voltage is actually 240 volts. For those of you that have ever taken a family trip to Europe and you've brought your devices with you, you had to, prior to going to Europe, buy an adapter to use those devices while you're in Europe. The reason why is because the RMS voltage in Europe is actually twice as much as it is here in the United States. So you have to adapt for that when you go back and forth between the two continents, for example. Okay, I'm going to go ahead and conclude this here as a part 2 of the lecture. We'll do briefly a part 3 where I'll lead you through the remainder of the examples.